Okay, so this problem looks a lot like a problem from your homework 5, um, but it's a little different. We still have equipotential surfaces, so that means these surfaces are really like this is looking at a side view, so these surfaces like go back. Um, so like this, right? And each one goes back. And so it's like a bunch of surfaces, and we're just looking at it from the side. So each of these, along this plate, I would say, right? Each one of these dotted lines represents a plate, and and so or like just a spot in space where the potential varies from 0 volts to 20 to 40 to 60 to 80. So one thing I always think about and I always label is this plate is going to be the positive plate because it's at a higher potential because it's at 80, and this plate, let me just erase these for a sec. So this is going to be the positive plate, the more positive side, and this is going to be the more negative side. This voltage is less than this voltage, and so I know my electric field is going to point from positive to negative. So I know my electric field inside these spaces is going to be a constant and it's going to point to the left. The other thing is here, each of these uh, particles, right, is going to be a proton. So that's important. On your homework last time, it was an electron. So if I think about a proton and I have a proton here, right, a proton is going to be attracted to the negative side, to the negative plate here. So for me to do positive work, I'm going to have to push this way to the right. If this, I don't have to do any work to get the proton to move towards the negative plate. It's going to do that on its own because it's attracted to the negative plate. So if it's going to the left, it's going to be negative work. And so it's going to be negative work over here when it goes from here to here, and then it's going to be positive work, meaning I have to push it to be able to push it towards the positive plate because it doesn't want to go, so I have to do work. So let's just start with 3, right? So 3, when it starts here and goes this way, it's going to be, I'm just going to call it 2. So I'm going to call this plus 2 or minus 2 because it's negative work, right? And then 1, 2, 3, 4, plus 4. And I'm not really using any units or anything. I'm just using my separation between this plate to this plate is 20 volts. This way to this plate is 20 volts. And so that's the potential difference. So like if I think about work, it's going to be potential times distance, or so I can just, since all the units are the same, my distances between these plates are the same. So I'm just going to just make up some units. So I'm going to move 2 places, so minus 2 and then plus 4. So this is going to give me plus 2. So that's how much work I'm doing, plus 2 units. My next charge, I'm going to do this one. So it's going to be 2. So this one I'm going to have to push my proton from here to here because it's going towards the positive. It doesn't want to. So I'm going to say that's 3. So it's going to be plus 3 and 1. I'm only pushing it 1 unit, so it's going to be plus 1. So my order is going to be, let me just erase. I hate that I make these lines because I rush in my writing. So my order is going to be 2, 3, and then 1. So 2, 3, 1. Oh, that would be the order. I think last time we had to rank them. Now we actually have to do the calculation. Sorry about that. So I'm going to say, okay, well, I have an electric field, and so the separation distance between the equipotential surfaces is 5, then the magnitude and direction of the electric field. So I'm doing magnitude, so that's the number, and then direction is the direction. So I already said like my electric field points from positive to negative always. So I know it points to the left, so I can get rid of C and D here. So I just have to figure out whether it's A or B. So I know that electric field times distance is equal to potential. That's something you can memorize, or I know a lot of times I always think about equations by like my first principles. So one of the things I know is that like the electric field is equal to KQ over R squared, right? For just like so I just use that for units, right? I forget about K, I don't care about K, I just know it's Q over R squared is the thing I know. And then potential is equal to KQ over R. So if I don't have an equation and I'm not sure what I'm doing, like I just go back to these equations that I know. I know an electric field, a charge creates an electric field, so I know it's only 1Q. I know with potential, a charge creates potential, so it's just 1q here. 1 over r squared for electric field, 1 over r for potential. So that helps me to know that I know I need to multiply by an r, or a length, to get the units right for potential. So that's why I can come up with this if I forget or don't have it on my equation sheet. But now I always like to show I'm solving for E. I'm solving for the electric field here. So I'm going to say E is equal to the potential over the distance. Okay, so if I go back here, let's see, it's saying so I did all this, but I didn't really have to. So that's just like your homework. So I answered your homework question from homework 5 using this picture. I guess just to show you that when I just worked this out earlier today, and but that it's different because this one's a proton, so the order would be different. But to calculate the electric field, I can use potential over distance. So I just picked these 2 plates, so the leftmost plate and the rightmost plate. So my difference, my delta V, is going to be 80 minus 0, so I'm going to have 80. So 80 volts divided by the distance, and each of these is 5, so 5, 10, 15, 20, over 20 meters. And so then E is going to equal 4 volts per meter. And like I said, it's going to be to the left, so it's going to be B. All right, so now we can do 2. Oh, there was a rank. So my rank the paths, so we did that. So that's number 2. So we're going to be 2, 3, 1, so that's going to be D. Okay, let's do another one. Maybe we'll do a page per video. Okay, so this is similar to your homework 5 also, but now they added, to try to trick you, they added in this charge up here, right? And what students typically do is they they see a charge here and a charge, 2 charges on this axis and then a charge up here, they think that they're going to have to do components. They're going to think of vectors, but you don't want to do that. We're looking at electric potential. So whenever I have electric potential, I know it's a scalar. So immediately you should say scalar. I love scalar because I don't have to worry about components. I can just use my equation. So my equation for electric potential is equal to KQ over R, right? And it's asking me to find the electric potential at the origin. So this is where I'm interested in, right? So if I were to, what I really want to do is calculate the potential for each one. And so the way I do that is I say, okay, my total net potential is equal to the sum of each one, right? So the sum, mathematically, I can make the sum symbol, right? KQ, say I, because I'm just representing each of these. So this would be 1Q, a different Q, a different Q. In our case, it's the same over Ri. And what does this mean? So whatever Q I have, 2Q, 3Q, whatever that is here, over the distance to the origin. So just drawing it, right, what I want to do is think about, I think I did this for your last homework, is if I start here and I'm thinking about this charge, right, I'm thinking about the potential caused by this charge at this location, at that spot. All right, and that's what this formula means. It says for this charge at a distance r away, I can calculate the potential here, right, on this sphere around this charge. I can calculate the potential using this. So I'm going to have, this is my 1 plus, I'm going to have this one. Here's my charge, right? And I'm going to have this potential that's like that, right? So that's going to be the term for the second charge, right? This is my 1 charge, this is 2, and then plus my 3 charge is going to be here. So I'm going to have, and that looks further away, but it shouldn't be. And so I'm, again, calculating the potential due to each one of these at these points. That's what this means, the potential for this situation, for this charge, plus this charge, plus this charge. Now, the great thing is each of these is A away, right? And each of these is the same Q value, plus Q, plus Q, plus Q. So V net then is just equal to KQ over R, or KQ over A, and I can multiply it times 3 because they're all the same. So if I plug in, right, I'm going to have 3 times 9 times 10 to the ninth. I forget the units, but we could figure it out, but I'm not going to do it right now. And times the charge, which is times 1 times 10 to the minus 8 coulombs, divided by my 1 meter. That's my A. Little a meaning the distance from here to here. And so I guess we should go back and think about what are our units for K. So K is going to be, I know my potential is in volts. So K, just if I want to work through what the units are going to be volts. And then to get K alone over here, right, I need to multiply by A. So that's going to be times meters divided by Q. So volt meter divided by coulomb. And then I would be able to cancel my coulombs here, be able to cancel my meters here, and I'm left just with volts. So if so V is then going to equal 3 times 9. So 3 times 9 is 27. So I know that. And then I've got 10 to the ninth and 10 to the minus 8th here. So I know I'm going to have an extra 10. So times 10 volts, so that's just 270 volts. Right here is C. So I've got C. And I'll stop. We'll call this video 1 of the review.